So we started chapter 9 in the last class and went over some basics of what is hypothesis, what is null hypothesis, alternate hypothesis, and then type 1, type 2 errors. So today we'll look at some problems, some examples. So I'll start with one of the solved examples, 9.8. So Jeffrey, 8-year-old, established a mean time of 16.43 seconds for swimming 25-yard freestyle with a standard deviation of 0.8 seconds. His dad, Frank, thought Jeff could swim faster using goggles. He bought new pair of expensive goggles and timed 15 different 25-yard freestyle swims. For the 15 swims, mean was 16 seconds. So basically conduct hypothesis test using alpha 0.05 to test if those new goggles had any impact. So 16.43 seconds is the time to beat, and the average of 15 swims was 16 seconds. 16 seconds is obviously less than 16.43 seconds. So one may look at the average and feel that it is an improvement, but who knows, like you take a sample again, the numbers may fluctuate up and down. So hypothesis test will help us figure out things by taking into account various things like sample size, variability, mean, and other things. So I'm going to write this down. Only one of these two hypotheses is going to be correct. In this problem, mu0 is 16.43. Sigma, based on the past experience, is known, 0.8 seconds. Sample size is 15. X bar calculated from these 15 swims is 16 seconds. Alpha is provided as 0.05. If you think of this normal distribution of X bars, which is average swim times. So the function we have been using is z.sum.test. This gives you a p-value of 0.01868. And if you refer to rejection rule, you can reject if p-value is less than equal to alpha. You cannot reject otherwise. We can say since p-value is less than equal to alpha, which is 0.05, we can reject HO. So in the beginning of the chapter, I mentioned that you are starting with some theory or claim or hypothesis, and then you test that using data, and then you have a decision, and decision here is to reject HO. All these things that we do in statistics, ultimately we have to convert that into a language that anybody can understand. So it's important always to write down what is your conclusion. So conclusion here is, we can conclude with 95% confidence that the new goggles improves Jeff's mean time to swim 25 yards to less than 16.43 seconds. So earlier, whatever we did in chapter number 8. So I'm going to open a new file. So new file, first one, and we'll save that as chapter 9. I will close chapter 8. So chapter 9 is now here, and we'll clean this up. And we need library that we used earlier, BSDA. So z.sum, so I'm just typing whatever I wrote. So select that, and then supply all these things, mean of X, and once you run that, you get this p-value 0.01868. So this is what we had. The mean throwing distance of a football for Marco, high school quarterback, is 40 yards. Standard deviation 2 yards. Team coach tells Marco to adjust his grip. Coach records the distances for 20 throws. So that is the sample size. And mean X bar is 45, alpha is given. So we want to test to find out if there is any improvement because of whatever coach has suggested. First of all, we write down what is null and alternate hypothesis. So with the new grip, obviously expectation is that Marco will be able to throw more than 40 yards. So that's what we are testing for. So when we write HA first, because that's what we are testing. And opposite of that is HO, less than or equal to 40 means no improvement. Mu 0 is 40, so this number here is mu 0. Sigma is given 2 yards. They took a sample size of 20, so 20 throws, and they got an average of 45, alpha of 0.05. One tendency among people who have not learned statistics is if you are trying to figure out whether your average is better than 40 or not, people simply look at the average. You look at the average, it is 45. 45 is better than 40. It's more, so it's better. Somebody may jump to a conclusion that the new grip is working because that's what the data says. X bar is 45, 5 yards on an average more than 40. But we need to remember that those 20 samples are just 20 samples. That's not the population in the long run. And if we take into account not only that, okay, that number is more than what we need, if we take into account the variability, sample size, confidence level, we are able to make more informed and more scientific decision. So that's the whole idea behind carrying out hypothesis testing and not jumping to a conclusion just based on the average. Average is always misleading. It is only one number. It is something that will never tell the full story. So if you input all these in R, so we'll copy paste so that we don't have to type again. So basically we are interested in this p-value and we get the p-value. So the p-value that we got is 2.2. I just want to write exactly what we saw there. So this is 2.2 times 10 to the power of negative 16, which means you start with 0 point and then 15 zeros, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and then you have these numbers 2 and then 2. Almost zero, like the probability is almost zero that this is a rare event. Rare event means that it is very different from what we had in the past. So in the past, Marco was throwing football 40 yards regularly, but with this new grip, he is achieving something very different, something which has a very, very low probability. So that means there has been a shift, total shift, based on the new method. So we can write, since p-value is less than or equal to alpha, we can reject HO. We can reject null hypothesis. We can reject null hypothesis means, again, this is not correct, This is correct. So there is an improvement. One thing you'll notice by now, we always talk in terms of null hypothesis, HO. We don't say we accept or reject HA. We never talk about HA. We always talk about the null hypothesis getting accepted or rejected. So that's the convention we use. Anytime we are doing hypothesis testing, we always talk in terms of HO. But obviously, when we conclude, we bring in all the details. Both of these examples were situations where we were using z.sum or normal distribution. Test for mean, sigma known. Sigma was known. We used normal distribution using z.sum.test. Let's look at some examples of second type. Jasmine has just begun her new job on Salesforce of a very competitive company. Sample of 16 sales calls. It was found that she closed contract for average dollar value of 108 with standard deviation of $12. Test at 5% significance. So 5% significance is another way of saying alpha is 0.05, or confidence you want is 95%. That population mean is at least $100 against alternative that it is less than 100. Company's policy requires that new members of Salesforce must exceed average of $100 per contract during their trial employment period. So can we conclude that Jasmine has met this company's requirement with 95% confidence? So basically, she has to do better than $100, and the average she got is 108. But then if we take another sample, instead of 108, it could be some other number. So how do we conclude? So we make use of t-test. We are testing if she is able to close contracts worth more than $100, and null is that mu is less than equal to 100. So in this example, mu 0 is 100. So this value is 100. And you have x bar, you have 108, and we are looking in the upper tail. So we use tsum function, tsum.test. And alternative this time is greater than. So this is what we need. So if you enter this, you get a p-value of 0.00. You can round this to 9. So since p-value is less than equal to alpha, we can reject HO. So HO is rejected. So this is true. So she is definitely fulfilling the requirements of this new job. Example, this was 9.9, and I will copy this format to save time. The only thing is now it is not z.sum but t-sum. We use t distribution, and these numbers will change. 108. So this is the p-value, 0.008798. So this I rounded to 0.009. Now if you recall in chapter number 2, if I click on chapter 2, so I collected some data from you. We created this histogram, like how many steps students at UMass walk to get an idea. And we had roughly from 1,000 to 25,000 steps. We want to use this data to test whether test whether business statistics students at UMass Dartmouth walk more than 8,000 steps each day. So that's what we want to test. We can set up HO and HA that mean number of steps is more than 8K. Students walk more than 8,000 steps. That's what we want to test. So that goes to HA. And opposite of that is mu is less than equal to 8K. So I'm going to copy that here, the data that we had collected. If you do summary of this data, just to get a feel of what data we are looking at, summary of steps, you can see the average is 8.074, slightly over 8,000. And then you have minimum, first quartile, median, and all other values. So it is going to be close, like this is just one sample. You take another sample, maybe it becomes less than 8,000. So we cannot rely on average only. We cannot say that because this mean is more than 8,000, hence the proof that students on an average walk more than 8,000 steps every day. So we cannot conclude that. We have to bring into the equation what is the sample size, what is the variability, and all other things, what distribution we want to use. I will copy and paste the T, because this is going to be t-test. Average of these values, we are not given, so we have to calculate. And the way we calculate is, we find mean of steps. Because all the data is in steps, and these numbers they are in thousands. One means 1,000 steps. Second student was 4,000 steps, and so on. So that is mean of steps. Standard deviation again will be calculated from this. So SD, standard deviation of steps. Sample size, 27. Confidence level, let's say we want 95%. And this is against 8,000 steps. And alternate hypothesis is that students walk more than 8,000. So we'll keep that. So you run this and you get an answer. P is 0.4654. So if I write down using T distribution, we got since P value is not less than equal to alpha, we cannot reject HO. So this time we cannot reject because P value, based on the data, the P value we get is not something which is a rare event, like it's not very far away from 8,000. So distribution of 8,000 steps, you have it, and this P value is such that it doesn't indicate anything special. So that means they are not walking more than 8,000 steps. So we conclude with 95% confidence that business stat students at UMass D do not walk more than 8,000 steps each day. Based on whatever data we have, we cannot conclude. We'll look at example 911. The mortgage department of a large bank is interested in the nature of loans of first-time borrowers. This information will be used to tailor their marketing strategy. They believe 50% of first-time borrowers take smaller loans than other borrowers, and they perform hypothesis test to figure out if percentage is same or different than 50%. So HO equals 0.5 and HAP is not equal to 0.5. So that is already given there. So they sample 100 first-time borrowers and find 53 of these loans are smaller than other borrowers. But ultimately, we want to reach a conclusion whether we can reject this null and alternate hypothesis. So this can be very easily done on a calculator or Excel. I'll show you how you can do much faster in R. We can write down that HO, we are saying equals 0.5. We will use prop.test for proportion test. If you need to see what it means, you can use a question mark with prop.test, and the fourth window becomes help window, and it provides details of each feature or attribute within this function. Also provides some examples. So we can enter all the information that we wrote. So two-sided should be two dot-sided, and once you run that, you get the p-value 0.5485. So we can write this p-value. And we can conclude, since p-value is not less than equal to alpha, we cannot reject HO.